We've been talking about organic chemistry, and last time during lecture, we were finishing up sort of alkenes and some reactions that happens with alkenes. A reminder, alkenes have the carbon-carbon double bond. They do give rise to, as we talked about, isomers, which could be cis isomers, where the groups are on the same side of the double bond. There could be trans isomers, where they're on opposite sides of double bond. And we finished up sort of talking about addition reactions, which is what alkenes undergo. And pretty much all addition reactions pretty much work the same way. You have an alkene that basically has the double bond, and that really is the sort of only thing that you should worry about. We may add two things here, and what always happens is just that this guy becomes a single bond, and then basically we add in one guy to each of the carbon. Now there are symmetrical additions like we talked about, where you add something like Br2, Cl2, H2. And it really doesn't matter where those guys go. They should go on either side, basically. There's also unsymmetrical additions, like when we add water, which is H and OH. It's sort of how we add it, or like HBr or HCl. It can make a difference in those cases as to where you add the hydrogen, if there is sort of a difference. So, for example, if we had a double bond, maybe like this, so we'll do something like that. And if we were to say, not draw an arrow, but add something like water here, when we do add water, it's H and OH. In this situation, we would still look at the double bond. We would still make it a single bond. Everything will still remain exactly the same. As we talked about, you're just going to make double bond into a single bond. But now what we want to look at is there is on this carbon two hydrogens that are attached to it directly. On this carbon, there's one hydrogen, and Markovnikov's rule is that the hydrogen that's being added from, say, the water here should always end up at the carbon that had the most hydrogens to begin with, which means it's actually the carbon on the right should get the hydrogen, and the guy there on the left should get the hydroxide or the OH group. Now, if it doesn't make a difference and they both in the double bond have the same number of hydrogens, you could just put it on either side you like. It's basically the same deal. But if there's a difference in an unsymmetrical addition, you do have to kind of look at that. Any questions on any of those reactions and stuff we talked about there? Okay, to finally finish up this never-ending chapter here, which is 11, we're going to talk about aromatic compounds. Aromatic compounds are really benzene-containing compounds. Benzene is a 6-carbon ring, but it does have 3 double bonds in it. So it's got 3 double bonds in it. That means there's just one hydrogen, basically, at each of those carbons. And it gives us a form of C6H6. You could draw a resonance structure, if you remember from bonding, where we just move the double bonds to the other options, which would look something like this. But a lot of times, especially in your book as well, they will sometimes just draw sort of a circle in the middle to indicate that those double bond electrons can move around, and they can be at any part of any of those things. So all 3 of these things are essentially equivalent to each other. They're all basically pictures of benzene. It should not be confused with what we saw earlier, which is cyclohexane, no double bonds, nor should it be confused with cyclohexene with 1 double bond. This guy's got 3 double bonds. So benzene has 3 double bonds. So these are different things. This is cyclohexane. This is cyclohexene, and then these guys are benzene. So benzene is sort of the functional group of aromatic compounds. It basically has a flat structure because of those double bonds that are happening there. And those double bond electrons can move all the way around. Now, with benzene, there are certain historical names that still do sort of come up when you have a benzene ring and certain groups attached. So, for example, these are three common ones that come across. If you have a benzene ring with a methyl group on top, it is known as toluene, and that's sort of a historical name that people still use today. If not, you could just call it methyl benzene, if you like. And that's another name that's called. A benzene ring that has an NH2 group, a nitrogen-containing group, is known as aniline, and also that is a name that's also commonly used as well. And this is one that's an alcohol here. And once again, that is a benzene ring there with an OH, and that's what is known as phenol. So that's the name that's commonly used. So you should be familiar with phenol and toluene. Again, they do pop up still a lot. And aniline, as well. But I would say toluene and phenol are the two that sort of pop up the most, I would think. So how do we name these things? We do pretty much follow the normal rules like an alkene or a cycloalkene. If we just have one group attached, mono-substituted, that would be just a group, and then benzene at the end of it. So that is how we get to chloral benzene. There is no need to give the number where the chlorine is because there's just one group attached. So it's assumed that that's always going to be carbon number 1. When we do start to get groups attached or multiple groups attached, we do need to give some numbering. So this would be 1,2-dichloral benzene. The nice thing about a benzene ring is because it has the 3 double bonds, you pretty much could go left or right in terms of the numbering. You'll always go through the double bond, so it doesn't really matter. In this case, because of the 3 double bonds, either way you go, you will get there. Also 1 and 3 here is our dichloral benzene, and our 1 and 4 positioning here is our dichloral benzene 1 and 4. These positioning on the ring here does have special names as well. The 1,2 positioning is what is sometimes referred to as the para positioning, or just P. So instead of the number, sometimes people will just say P dichloral benzene or para dichloral benzene. The 1,3 positioning of those groups is what is known as the meta positioning. And again, sometimes people will use meta instead of the numbers, or just M dichlorobenzene instead of the numbers. And M, again, basically telling you that it is the 1,3 positioning. And we also have ortho, which is our 1,4 positioning. So these are, again, sometimes used in place of the numbers. And sometimes they'll just use the whole name, or they'll just use the name or the letter. And I'm pretty sure I did that one backwards. It's on mine. So let me read you those there. Sorry about that. This is the ortho positioning. There you go. I just wanted to. It's close, almost, sort of. Para, which would be P. There you go. All right. Well, that didn't feel right. It just didn't feel right sometimes, sometimes don't feel right. All right. So ortho 1,2 positioning, meta 1,3 positioning, and para 1,4 positioning. So again, this would be sometimes just written ortho dichloral benzene. So if we look at some of these guys that have multiple guys involved, let's just see how we get to these names. The aniline part of the name here is based off of pretty much this part of it. That is the aniline part. That's that historical part of the name. And then you can see that the group there is attached right there. Since this is sort of the historical name, we would give that position number 1, position number 2, position number 3, and that is where the 3-bromo aniline comes from. Once again, here, if we sort of highlight the historical part here, that's an OH with a benzene ring, so that is going to be the phenol part of the name. And once again, our OH is going to be carbon number 1 in this case. Now, if we go clockwise to the right there, we would have groups up numbers 4 and 6. And if we go left or counterclockwise like they did there, you can see we will get smaller numbers of 2 and 4. So in this case, we would want to go counterclockwise in terms of the numbering. That would give us 2-chloral, or actually 4-bromo because it's alphabetical. So 4-bromo, 2-chloral, phenol in this case. And lastly here, we have our toluene, which once again is our CH3. And this part of it is the toluene part. And then we have our groups that are there. We have obviously 2 bromines here, which is our dibromal, and we have 1 chloral. And again, numbering here, it really, I don't think in this case matters which way you go. You can go clockwise or counterclockwise. You'll end up with kind of the same numbering no matter which way you go. And that would give us alphabetically 2,6-dibromal, 4-chloral. Remember, alphabetically, regardless of prefix. So that's why the B here comes before the C in this case. Any questions on any of those there? So like I said, sort of phenol, toluene, it does really still pop up a lot in books and stuff like that. Those sort of historical names. All right, so let's take a look at this one here. I want to select the correct name. So once again, the entire thing here is going to be benzene. And obviously we have a chloral here, so that's going to be chloral benzene, which should be this one. Once again, in this case, we do not need the number because there's just one group attached. Here, we're going to look at this, and we could have gone with the historical name, but if we didn't go with the historical name, we'll just go with this as our benzene. We have a methyl group there and a methyl group there, which would give us dimethyl, and you could choose either one. So 1, 2, and 3. So 1,3-dimethyl benzene looks like a winner. That would be the meta arrangement there, meta-dimethyl benzene. You also could have called it, took this whole thing as toluene as well at the end of it with the methyl group. So a few different names you could have sort of named this particular one. This would be more the IUPAC name here that we see up on the board. Any questions on that one there? Yeah. If you do have a benzene ring, the methyl doesn't necessarily have to be at the top position, but if you just basically have a methyl somewhere in there, it would be. That's toluene, yes. Yeah. No matter where it's at, yeah, if you have basically a methyl group with a benzene ring, it's historically called toluene. Sort of IUPAC name would be methylbenzene. But that is again a sort of a common name that will still be used a lot, still today. Stuff like that. Whoops. Any questions on that there? All right. Finally, that chapter. All right. Okay, we're off to chapter 12, which covers a lot of the remaining sort of groups, some of which we previewed here during discussion. So we'll officially come through it here today. We're going to talk about alcohols, thiols, ethers, aldehydes, and ketones in this chapter. So first off, alcohols, thiols, ethers, aldehydes, and ketones. These are all different organic groups. They all have some different. The alcohol's functional group is the OH group. The thiol is the SH group. The ether is a carbon, oxygen, carbon functional group. The aldehyde is a carbon, oxygen double bond with a hydrogen. And the ketone is 3 carbons in a row. And the center carbon has a double bonded oxygen. So these are the functional groups. For each of these guys. And again, depending on which functional group we're looking at, we'll give some of these guys some different properties in terms of solubility in water or being able to sort of have boiling points higher or lower than what we see in alkenes. And so we're talking about individually here. So once again, our functional group for our alcohol, the OH, carbon, oxygen, carbon run that you need for an ether, and our thiol, our SH here. This is a alcohol that we just saw with our benzene, and that is sort of a special group, which is again known as phenol, which is sort of a aromatic alcohol. And again, our SH and our COC. By the way, speaking of benzene, why I think about it, and we just talked about it, if benzene should happen to be sort of a group and not really the main thing, just draw some weird thing here. And maybe it's sort of a group that's hanging off of it. If benzene is a group, it is known as phenol. If it is a group, if you do have benzene. So if you see phenol, there is a case where benzene may not be the longest carbon chain, like my squiggly lines there shows. There's a lot more carbons attached everywhere else, and is sort of acting as a group. Very rarely we'll probably come across it, but you might occasionally do. Benzene can be like a group that's attached if it's not the main thing that's there. So for example, maybe there's a OH or something else attached over here that makes this sort of the main part in the benzene is a ring that's attached. So it's sometimes referred to as phenol if it is a group, not the main thing. So let's talk about alcohols first, and again, properly how to name it. When we do deal with alcohols, it is always the longest carbon chain. It has to contain the OH group as part of it, and we basically drop the last part there and put OL. When you get to about 3 or more carbons, you also need to give the location of the OH group, much like what we do with the double bond or triple bond. The OH group does get the priority here. So in terms of numbering the chain, you always want to number whichever way will give the OH group a smaller number. The simplest alcohol you could have is a 1 carbon alcohol. And this is known as methanol. And because it only has 1 carbon, you don't need to give a number. You can then have ethanol, which has 2 carbons and based off of ethane. You also do not need to give a number here because frankly, there's only really one option as to where that OH group could be. But when you do get to 3 carbons, you do need to start giving some numbers because you could have this guy here, which is 3 carbons based off of propane. And because it's an alcohol, it is propanol. And the OH group is located at carbon number 1. So this is 1 propanol. And that would be different than if we had the OH group there on our 2nd carbon. This also would be 3 carbons with an OH group, which would be propanol. But the OH group is at carbon number 2. So this is 2 propanol. So 3 or more carbons, you do need to give the location for the OH bond or where the OH is located. And again, you want to make sure that it is the smallest. One of the properties of alcohols is because it does have this polar group where the oxygen is more negative and the hydrogen is more positive, it does make it fairly soluble in water because it can participate with water and do what's known as hydrogen bonding between the oxygen and the hydrogen. That means most alcohols or very small alcohols are pretty soluble in water, like methanol, ethanol, and so forth. Propanol. Solubility does decrease right around 6 carbons. So when you have 6 carbons or more, the solubility pretty much drops way down because basically you have a more non-polar parts than you do polar parts. So it gets in the way when you do it, when they try to interact with each other. All right. So if we're going to name this, take a second here and name this and see what you come up with. Why don't you also draw, let's do 4-chloral 2-hexanol. Okay, let's take a look. So we'll do longest carbon chain here. We could go 1, 2, 3, 4, 5, 6. Again, that does contain the OH group. You could also get 6 if you start here and go that way. Doesn't really matter which way you choose. So it does look like 6. So that is going to be hexane, but since it is an alcohol, it will be hexanol. We do want to give the OH the smaller number. We would want to start numbering right to left in this case, because that gives the OH the priority and the small number. That means that this would be 2-hexanol. Wow, I think I almost did the same one. And that means that this would be 1, 2, 3, 4, and a carbon number 5. There would be a methyl. So this would be 5-methyl 2-hexanol. Oh, well. Any questions on that one there? All right, so when I up with apparently just like that one, apparently. So that's going to be hexanol, which is 6. Since I'm drawing it, I'm going to go left to right and make my 2-hexanol, my OH group right there at carbon number 2 for me. Since that would be carbon number 2, should be carbon number 4, where there would be a chlorine. And now at this point, everything else here should just be hydrogens to get to 4. That's going to be 3. That's going to be 2. That's going to be 1. That will be 2. 2. That will be 1. And that will be 3 in this case. Any questions on either of those? Yeah. I missed the first one. You 2. Yeah, it would be incorrect because in this case, the group, which is the alcohol, the OH, it's priority in terms of numbering, just like the double bond and triple bond kind of take the priority as to which way you go. So pretty much always, if there's a functional group and you need to kind of give a number for the functional group, they always take the priority in terms of numbering. They should always be the smallest. Yeah. Other questions? Okay, so let us do these two here. What are the names of these guys? And then let's why don't you draw 3-methyl cyclopentanol. All right, let's take a look here and see how we're doing. So longest carbon chain, 1, 2, 3, 4, 5 has the OH. We again could get it if we went that way as well. So 5 carbons there with the OH will give us pentanol. Giving our location here going this way, we'll give that OH group the smaller number of 2. And again, we'll put our methyl group there at carbon number 4. So that would be 4-methyl 2-pentanol. Any questions on that name there? Coming to the guy on the bottom there, we got this whole thing here. That is one of those kind of historical guys that we talked about and saw a second ago. That is phenol. And that would make this guy carbon for sure. If you go counterclockwise in this case, that will put our bromine at carbon number 3, which should be the smallest number. So this would be 3-bromo phenol. Any questions on that one there? Again, this is not cyclohexanol because there's 3 double bonds. It has the benzene ring and not the cyclohexane ring that is there. Drawing, we're going to roll this way. This is cyclopentane, pentanol. So cyclopentanol is based off of cyclopentane, which is our 5-carbon ring. OL has an OH group, and really you could frankly put it anywhere you like. I'm just going to put it up there on top. And because I put it up there on top, that obviously means that carbon would be number 1. I'm just going to go clockwise in this case. Again, you could go counterclockwise if you prefer. And you could put a methyl group there, which actually would just be that. Do more of this, you can write it in, but it's technically just a line. Any questions on either of those there? Yeah. Yeah, for this particular one we just drew, you could have, for example, if you wanted to, laid up the OH there and then just went 3 spots from there and did a methyl group. It's really the same because it's all single bonded, which means if you just rotate this thing around, it becomes this guy. So it doesn't really matter in this particular case. There's no double bonds or anything like that in the ring to sort of give location of that. So wherever that guy ends up will be basically carbon number 1, the OH group. Yep. Other questions? It doesn't in this case as you're drawing it. So I went counterclockwise on the one on the left. You could have went clockwise as well because you're drawing it. You could actually go either way in this particular case. Yeah. Other questions? Okay. So obviously some alcohols and phenols. Ethanol, which is ethyl alcohol, has been known obviously as the good alcohol, I guess. That is the is made by fermentation of grains, sugars, and starches. By the way, we produce alcohols. We saw that reaction earlier today and last time. We actually make an alcohol right from a reaction of an alkene plus some water, basically, right? And that is basically how we produce an alcohol, is basically through that reaction. That hydration reaction is basically how we do produce an alcohol. As we see here, hydration reaction puts on the OH where our double bond was, and that creates our alcohol. Alcohols, again, like I said, are fairly soluble in water, especially small alcohols, but solubility does decrease. Also with alcohols, they pretty much have the highest boiling points because they basically can hydrogen bond with each other, with themselves. And hydrogen bonding is pretty much the strongest sort of bond, which is hydrogen bonding. And that means that alcohols typically have very high boiling points because of that. So because alcohols can basically hydrogen bond with themselves, it keeps them together very strongly, and it takes a lot of energy to get them to break apart. And that means it results in a much higher boiling point than, say, an alkane or an alkene, which cannot hydrogen bond. The more OHs that you have, the more soluble actually it will become as well. So just like if you make more carbons and hydrogens, it gets less soluble. You actually have something that has multiple OH groups on there. It gives it multiple places that can interact with water and actually increases the solubility. So the more OH groups that you have on there, the more soluble it will be. And again, as we talked about, kind of the less OH groups and more carbons, you will have less solubility. This is ethylene glycol, also known as antifreeze. It is 2 OHs there, which is why you can mix antifreeze with water, right, before you put it in your radiator and all that good stuff. Any things of water so you don't overheat your cockpit. To lower the freezing point in case you live in a really cold area, you have water in your cockpit. freeze because you have basically antifreeze in there, and it keeps the freezing temperature a lot lower than hopefully outside. Not in all cases, but that is basically ethylene glycol. BPA, some polycarbonate, also some alcohols here. And again, you're not going to be asked to draw any of these, but we do see our alcohols here. Also with our, really our phenols are here, is what we got there. All right. Let's talk a little bit about thiols here. So thiols are sulfur containing groups. They have the functional group of SH. SH is also a polar group. Sulfur is right below oxygen there on the periodic table. So it also is a polar group. So very similar a little bit to oxygen or the alcohols, but it cannot really high can, so it has a much lower boiling point. Sulfur containing, sulfur kind of stinks, as you can see there. It's found in things like cheese, oysters. They also put a little bit of sulfur containing compounds in natural gas just in case it leaks. You could smell it. Otherwise, actually, it doesn't smell natural gas. So they actually put some stuff in there to make sure you can smell it just in case it starts to leak. In terms of thiols, we are not going to name thiols, I think. So we don't even worry about it, I guess. But in case you would like to know how you name thiols, you basically, no, nobody wants to know. All right, just, we'll just forget that, put an X on that. Forget it. Never was on this page or anything like that. All right, jeez. All right, let's not learn anything. All right, we're not going to learn that either. Let's talk about ethers then for a second. But actually, let's go back to thiols real quick. I know. We want to talk about a reaction that's important with thiols, and there's basically two reactions that basically thiols undergo, and we'll see it probably a little bit later on. But if you take two thiols and you put them together, what happens when you put them together is it will go through an oxidation reaction. And in this oxidation reaction, it will lose H2. So this oxidation reaction, basically what will happen is the hydrogen on one and the hydrogen on the other basically will come out. So those guys get lost and we make H2. And then what happens is pretty much you start here and then you continue through here and just put them together, basically. The sulfur to the sulfur is always how they will connect. And you'll get CH3 on the left there, the sulfur, got rid of the hydrogen, got rid of the hydrogen, another sulfur, CH2, CH3. This makes what is referred to, this SS bond here, that is what is sometimes referred to as a disulfide bond or bridge. And it's important in amino acids and proteins as well. Some amino acids can make cysteine. People can make this disulfide bond. That also means that the opposite is true. If you take a guy that has been put together through two sulfurs or thiols, and you add hydrogen to it, the same thing is going to happen. They're going to break apart right there where they always come together. And basically the guy on the left gets a hydrogen, the guy on the right gets a hydrogen, and you separate them out. So if we were to do that, I'll just draw it down here, I think. We would go with the guy on the left, which is CH3S, and we're going to give him one hydrogen from here. Then the guy on the right gets a hydrogen, the second hydrogen, and we add the S, and then everything else stays the same. This is what is referred to as the reduction reaction here. Reduction means that it gained H2. So H2 goes out and you put them together to make that disulfide bond bridge, put H2 back in, they break apart. The connection between the two thiols are always between the sulfur and the sulfur. So it's always where they come together, and it's always where they would break apart if he broke apart. So H2 puts them together, take it out, put H2 back in, you break them back apart. Any questions on that one there? Okay, so for thiols, you need to know the functional group and you need to know those two reactions, basically putting two thiols together, which is the oxidation reaction, and breaking apart two thiols that have already been put together, which would be the reduction reaction, basically the opposites of each other, those two reactions. Any questions on that there? All right, then let's talk a little bit about ethers. Ethers have the functional group of carbon, oxygen, carbon is the functional group. And you do need to know functional groups of all these organic guys. So it contains this oxygen in the middle. It has a bent structure because really there are non-bonding electrons there as well, even though a lot of times in organic chemistry they're not drawn, but there are those non-bonding electrons on that oxygen. And it gives it that 4 electron pairs and 2 bonds, which is the bent or V shape. It has a common name by basically giving the groups that are attached and then laying up ether at the end of it. So we'll go with the common way of naming it, which seems easier. So for example, as we see on the bottom, here's the common way of naming an ether. You basically recognize this as an ether. You go to the right there, and that's a methyl group. You go to the left, that is a methyl group. If they are different groups, you put them in alphabetical order, but in this case, there's 2 methyl groups. So that would be dimethyl, and then you just put ether at the end of it. If you had something like this, CH3, CH2, O, CH3. Again, going to the oxygen, we have a methyl group. This is a 2-carbon group, which is a ethyl group. This would be known alphabetically as ethyl, methyl, ether. So basically you name the groups in alphabetical order and just lay up ether at the end of it. And that's much easier than the proper name, which is, in this case, it would be thoxyethane. We'll just do common naming here. Why not? So functional group for ethers, carbon, oxygen, carbon, you need those 3 guys together in that order. And then to name it, basically, if you identify it, the easiest thing, just go to the oxygen, go right, go left, figure out the groups that are attached, and then basically put them in alphabetical order. Any questions on that there? And that's what we see here. Looking at this example, again, this is our ether part there, carbon, oxygen, carbon. So carbon, oxygen, carbon run. To the right here, we have a 3-carbon group, which is propane or propyl. To the left, we have a 1-carbon group, which is methyl, again in alphabetical order. That's how we get to methyl ether at the end of it. So not too bad. Methyl propyl ether would be that guy. Obviously, so that's sort of the anesthetic that you sometimes will get. Over the years, they've sort of changed some of that to some of the hydrogen for fluorine, some less side effects sort of happen in the case of that, rather than sort of giving you a normal ether. Sort of mellows out some of those side effects, and also the flammability, which is really a good effect as well. All right, so why don't you draw these guys here? 3-pentanol, ethanol, diethyl ether. Let me add a few to the list here. Let's do ethyl pentyl ether. Let's do ethyl ether. Oh, it's right there. Don't do that one twice. Let's not do that. Let's then do okay, let's take a look, see how we're doing. We should know how to draw this. Also, that's going to be 5 carbons or 5. OL means it's an OH group, and the 3 means that is where it's at. So I'm just gonna maybe go like up above OH. Rest will be hydrogens, so we'll just fill in our appropriate hydrogens, 3 at the end, 2 there, 1 there, 2 there, and 3 there. You know, any questions on that? That obviously is a condensed formula, right? In this case, ethanol is 2 carbons, so we'll just do 2 carbons. OL means there's an OH group, and really at this point, just fill in some hydrogens, and you'll have the condensed formula. Any questions on ether? All right, so now with the ethers, you should hopefully know ethers has this arrangement. So really, if you're going to draw an ether, you might as well just start with the so this will really lay up an oxygen. And that really takes care of the ether part. The diethyl means there's 2 ethyl groups. They're both 2 carbons. So then you can just fill in the appropriate carbons on both sides. And now the appropriate hydrogens. So that would be 3. That would be 2. The oxygen doesn't get any hydrogen. That would be 2. And that would be 3. Questions on that one there. Same thing here. I'm going to start with my oxygen because it's an ether, and I'm just going to kind of put my groups. So pentyl is 5. So that is 1, 2, 3, 4, 5. I think I didn't go 6. And the other side is ethyl, which is 2. So 1 and 2. And at this point, we're just going to pop in our hydrogens. So 3 here, 2, 2, 2, 2, 2, and 3. Any questions on that one there? And lastly here, same thing. I start with the oxygen, which will take care of my ether part. Propyl is 3 carbons, and really you can put on either side. It doesn't matter if that's a question. You know, you could go left or right. Since you're drawing, you could do it either way. So I'll go 3 to the right, which will do my propyl. And butyl is 4, which means I will go 4 to my left and then fill in my hydrogens at this point. This guy needs 2, 2, 2, and 3. Any questions? For like the ethers, is that asking? Yeah. So if you want to do line structure here, let's draw it up here. You could really do the same thing, to be honest with you, like we did with the condensed. You could start with the I was gonna say 0. You can start with the O there in the middle, and we'll draw this one here. So then you could just draw a propyl group like a line structure. So that should be 3 carbons, so 1, 2, and 3. And then you should draw a butyl group, which should be 4 carbons, so 1, 2, 3, and 4. So it looks something like that. Yeah. So again, you kind of do it the same way, no matter kind of which one you're drawing, line, expanded, or condensed. That's a good way to kind of do it and just kind of put in what you need. Other questions? Obviously, if we were going to do it for our alcohol as well, you know, you would just draw the 5 carbons, 1, 2, 3, 4, 1, 2, 3, 4, 5, not 6. Take 2. So 1, 2, 3, 4, 5. And then on carbon number 3, 1, 2, and 3 in this case, you would have the OH. So something like that if you're doing line structure. Any questions on any of those there? Yeah.
So on the line, the OH, but on the written out when you just put O, you don't have to put H.
Are we talking about these two here? Are you talking about between these two, or? Yeah. Yeah.
OH. But on the you have an O in the middle.
Yeah.
So would that be an OH when you do the front? Or would it be O?
These are all. So what I just drew here. Yeah, because the ether doesn't have the ether's functional group is really the carbon, oxygen carbon. So it's really this carbon, this oxygen, and this carbon, which is what makes it an ether. It's the same thing here. It's really this carbon, this oxygen, this carbon, which makes it an ether. Yeah. As opposed to the alcohol, which is this OH group, which is why obviously you need the OH group there. Yep. Other questions? Okay. Use of alcohol, hand sanitizer, which we're familiar with a lot these days, contains ethanol about 60% by volume, as high as 85%. So alcohol also, as we sort of talked about a little bit in discussion as well, can be classified like we classify carbons as primary, secondary, tertiary. When we go to classify an alcohol, you always want to look at the carbon that has the OH attached, and really how many carbons are directly attached to that. So in this case, there's just one. You want to look at the carbon that has the OH attached and how many carbons are directly attached to that one, which in this case is 2, which makes it a secondary. And the carbon, once again, that has the OH attached, directly attached to that carbon is 3 carbons, which makes it a tertiary alcohol. So primary alcohol, tertiary alcohol, and secondary alcohol, then different reactions that take place, which we'll talk about or have talked about. So if we look at this one here to go through it, we have the carbon that has the OH attached. So at this point, we're looking to see how many carbons are directly attached to that one. So directly attached to this one is 1 carbon and 2 carbons, which would make this a secondary alcohol. This carbon is the one that has the OH attached to it, and directly attached to that is only 1 carbon, which means this is a primary alcohol. This carbon is the one that has the OH attached, and directly attached to it is 1 carbon, 2 carbons, and 3 carbons. So this would be a tertiary alcohol. So it is not really, you're not counting from the OH group, but you are counting the carbon that's directly attached to the OH group, and then how many carbons are attached to that. Any questions on how to classify those there? As I mentioned earlier, alcohols, because they do contain that polar OH group, they are very soluble in water because, again, they're able to hydrogen bond. And that's what makes it soluble in water, is that OH group, which once again, if we took something like methanol, minus and positive, works really well with our polar water, which is also negative and positive. And again, they're going to be doing hydrogen bonding here. And that ability to hydrogen bond with water makes it very, very soluble. That means if you take something like methanol and you mix it together with water, it will all mix and look like one layer. There won't be separate layers or anything like that, because they are very soluble. As I mentioned as well before, once you hit about 6 carbons or more, sort of on this end, like something that we have down here, this becomes very insoluble in water. And it's really because these alcohols have really 2 parts of their molecules. They have a non-polar part, which is where all the carbons and hydrogens are, and they have this polar part. So what happens when you have a ton of carbons and hydrogens, you have a really big non-polar part and this little small polar part. And the really big non-polar part, frankly, gets in the way. It's sometimes referred to, it just gets in the way of the water being able to get in there and interact well with that OH group that's on the alcohol. And you see solubility pretty much drop to almost nothing in that case. So kind of up to like 5-ish or so in terms of alcohols, you'll have some pretty good solubility with water, but then it does start to obviously drop off as well. So as you can see here, 1 through 4, slightly soluble. Then we get into kind of insoluble, and definitely after 6, you're kind of insoluble at that point. And it's really, the idea here is in order for something to be sort of soluble in water, what it essentially is doing is before anybody interacts with water, the water and the waters are basically attached to each other through hydrogen bonding as well. So you have to replace the water interactions with something that's very similar in order for it to be soluble. So as you get these really big molecules that have non-polar parts, they really just don't fit very well with the water molecules, and they're not able to interact really, really well. Do that. We have phenols. Phenols are slightly soluble in water. That's because they do have sort of that benzene ring attached there. They can react with water in sort of a acid-base reaction where the phenol acts as the acid, sort of gives away the H plus over there to the water that acts as the base. And it can be, were once used as antiseptics as well. They produce phenoxide ions. You don't have to worry about that, but they can kind of do that sort of reaction as well. But they're kind of bulky because they do have the benzene rings, so they're only slightly soluble, which usually when somebody says soluble, it's actually leaning more towards being insoluble than soluble, but a little bit of it will kind of mix, but not a lot. So usually slightly soluble in most situations. So we want to know which of these will be soluble in water. Will this guy be soluble in water? It will not, even though it does have the OH, we got this really big non-polar part, so it's going to get in the way. So probably no on that one. This guy will be, again, it has the OH big, so it's less than 5 carbons or so there. So we would expect it to be soluble in water. Any questions on those there? We're going to talk about a couple other groups here, and these are aldehydes and ketones. They also have some functional groups. So the aldehyde functional group is the carbon-oxygen double bond with the hydrogen. And the ketone functional group is a 3-carbon run that has the double bonded oxygen there in the center. So the simplest ketone is basically acetone or propanone, which is dimethyl ketone. It is a colorless liquid, you know, to remove nail polish that you open in the car. Smells a little bit, maybe. But sometimes they take out acetone. But acetone can be used as a solvent. It really cleans up things a lot in terms of those things. Aldehydes and ketones do have a carbonyl group. A carbonyl group is specifically talking about the carbon-oxygen double bond. So that is what the carbon group is. It is actually a polar group where the oxygen is more negative and the carbon is more positive between it. So both the aldehyde and the ketone have this carbon-oxygen double bond. And it cannot participate in hydrogen bonding, but it can hydrogen bond with something like water, for example, because it has that negative on top, but it cannot hydrogen bond with itself. It creates a really strong polar thing, which gives it some properties, ketones and aldehydes, by that carbon-oxygen bond there being slightly polar. Now, the aldehyde group has the carbon-oxygen double bond with 1 hydrogen. Now, the deal with the aldehyde group is it will always, 100% of the time, be at the end of the molecule. So you will always find the functional group for an aldehyde at one end or the other end. And the reason for that is it has the hydrogen here at the end. And as we know from bonding, right, hydrogen should only have 1 bond, 1 line, 2 electrons, which means it always has to be at the end. It can never be in the middle, otherwise it has too many bonds going to it. So you will always find that group at the end. One of the things we'll talk about is because of that, you don't need to give the location of where that carbon-oxygen double bond is, but it will always be carbon number 1, the numbering. So although you don't necessarily need to give the location when you name it, you should always consider it carbon number 1 in terms of numbering because it's the functional group. Now, unlike that, the ketone, which has the 3-carbon run, you will never find the carbon oxygen double bond at the end of the molecule because it needs 3 carbons in a row. So that carbon oxygen double bond will never be at the end of the molecule in a ketone. And that's a nice way to distinguish the two. If you see the carbon oxygen double bond at the end of the molecule, it's probably an aldehyde. And if you see the carbon oxygen double bond in the middle with like a couple carbons around it there, it will be a ketone. Now, this also will need to have a number when you name it. So you do need to give the number where the carbon oxygen double bond is located in a ketone when it does make a difference. So for example, here, if we just put some hydrogens on this guy, it doesn't make a difference. This is the only place it could be because you need 3 carbons in a row. There's only 3 carbons, and that double bond has to be in the center. This would be named based on 3 carbons, which is propane. And the way we name ketones is like it says there, ONE. So you put ONE at the end. So this is what is known as propanone, ONE, which is a ketone. And if we had our same guy over here, this also has 3 carbons, but it has the aldehyde group here. So aldehydes end in Al. So instead of propane, this will be propanal, Al, not to be confused with Ol, which is an alcohol. Al is a aldehyde. Questions on that there? So if you were to draw it line structure, as you can see there, you would put the double bond in, and you would want to put the hydrogen at the end of it. Otherwise, if you left the hydrogen off of there, that would assume that the end would be a carbon, and you would have just made a ketone. So it's important, if you do draw the line structure, that you do put that, because if you did this, this is now a ketone. Yeah, this is an aldehyde. I agree. All right. Once you get to probably about 4 or so carbons in terms of the ketone, you do need to start giving the number as to where the carbon oxygen double bond is located. And once again, you would want a number whichever way gives the carbon oxygen double bond the smaller number in terms of numbering for those guys. There are some common names for some of these guys here for our aldehydes. 1 carbon is formaldehyde. You might be familiar with it. We're not going to do common names. We are going to do the UPAC way of naming, which is Al. That is this guy. This is 2 carbons, which is based off of ethane. So this would be ethanol there. All right. So there's our butanol. And again, the common names are there in parentheses. I would say maybe you should be familiar with that formaldehyde is methanol, because again, formaldehyde is used a lot. As sort of a common name, especially in biology, they use formaldehyde, right? And all those kind of things. So I say you should recognize the formaldehyde and the relationship there. But if you were going to name it, you could call it methanol based on 1 carbon. All right, so why don't we try some here? Let's name this aldehyde. Let's also name this aldehyde. All right, let's take a look. So remember, we want the longest carbon chain that contains the functional group. So that is a 1, 2, 3, 4, 5. And obviously this is our functional group, which is the aldehyde group there at the end. So 5 carbons is based off of pentane because it has the aldehyde group. Pentanal, Al. You do not need to give the location of that carbon oxygen double bond, but it will be carbon number 1, which means my methyl group is at carbon number 2, and this would be 2-methyl pentanal, Al at the end. Yeah. Any questions on that one there? Coming through on the next one, we got looks like 1, 2, 3, 4, 5, 6 there. Don't go one more. So 6 carbons is based off of hexane. It is the aldehyde group, which is right there. So hexane becomes hexanal. In this case, where the carbon oxygen double bond is going to be carbon number 1, which means that would be carbon 2, that would be carbon 3, that would be carbon 4. As to where my chloral group is, that would be for chloral hexanal. Any questions on that name there? All right, so drawing, we're going to do the same thing. So hexanal, we're going to go with 6 carbons. 1, 2, 3, 4, 5, 6. Now, because you're drawing it, I see Al, which tells me it's an aldehyde. You could put it at either end, but I'll just put mine here. And because I put that there, that would be carbon number 1 for me, which means that carbon number 4, there should be a methyl, 2, 3, and 4. And just like normal, everything else here will be hydrogen. So we need 1 there, a couple there, a couple there, and we should be good. Any questions on any of those there? All right, then let's talk about officially here naming ketones. Naming ketones, basically drop the last part of the alkane name and put ONE. As I mentioned earlier, when you get about 4 or more carbons, you do need to give the location of the carbon oxygen double bond. Before that, you really don't need to do so. So why don't we try this one here together, and then let's also do maybe this guy here like that. All right. And then we'll also draw one. Why don't we draw the 4 chloral 2 heptanone. All right, so let's take a look at these together since we're getting to the end, just to see how we do it. Longest carbon chain, I recognize hopefully right about here is my ketone group. So it needs to contain those guys. So that is 1, 2, 3, 4, 5 if you go straight across. Also 1, 2, 3, 4 if you go down, also 5. So again, it doesn't matter which way you go. 5 is based off of pentane. Because it's a ketone, pentane becomes pentanone, ONE. In this case, we do need to give the oxygen double bond, and we want to give it the smallest number. So we would go right to left, which would be 1, 2, 3, 4, and 5. That means that our carbon oxygen double bond's at number 2. So this is 2-pentanone. Because I locked in my numbering going this way, my methyl group would then be at carbon number 4 here. So that would be 4-methyl 2-pentanone. Any question on that one there? Coming to my line structure, once again, this part right here is the ketone. So that is the case you can't recognize it. That is 3 carbons in a row with the double bond in the middle. That means the longest carbon chain that contains that will be 1, 2, 3, 4, 5, 6, 7. And you could also get 7 if you went up instead of down there at the end. So you could get 7 either way. 7 is based off of heptane. I was like, I just make these things up in my head here and get the same one. Heptanone, ONE. We would want to give the location of that double bond, which would be 1, 2, 3, 4 if we went that way. 1, 2, 3, 4 if we went that way as well. It doesn't make a difference here which way we go to get to the double bond. Which way do you think we should go in this case? So since it doesn't make a difference for the double bond, the next important thing would be the group that's attached, right? So going actually left to right would give our group the smaller number. So we would want to continue to number this way. That would then mean that this is 4-heptanone And our methyl group, right, which is hanging off of here, would be at carbon number 2 in this case. That would give us 2-methyl 4-heptanone. Any questions on that one there? Lastly, here we got heptanone, which we just did. So that is 7 carbons. 3, 4, 5, 6, 7. 2-heptanone means my double bond's at carbon number 2. And since you're drawing it, you can either draw it to the left or to the right. I'm going to call this carbon 1 for me. So my double bond's going to go here. So that takes care of my 2-heptanone. Because that's going to be number 2, that means for me, number 4 would be here, which would be the chlorine. And at this point, everything else needs to get the 4. So that is 2. This guy needs 1. It needs 3. This guy needs 3. Yeah. Any questions on that one? By the way, before we call it a day here, what would that be called? First off, is it an aldehyde or a ketone? It is a ketone. That's a carbon. That's a carbon. That's a carbon and a double bond. So that is the ketone right there. And that whole thing is cyclohexane. So because it's a ketone, it goes from cyclohexane to cyclohexanone. Yeah. So cyclohexane becomes cyclohexanone, which is a ketone. Again, right there is your ketone, basically. Any questions on any of those? All right, we'll lay it up there.